Hello, Algebra 2 students. Today we will be doing 10.5 notes, find probabilities of independent and dependent events. What are independent events? Independent events are two events where the occurrence of one event has no effect on the occurrence of the other. An example could be, let event A be rolling a six-sided die, and let event B rolling or flipping a coin. Rolling the die and getting some result is going to have no effect on whether you get a heads or a tail. So those are two independent events. If A and B are independent events, then the probability that both A and B occur, so the probability that both A and B occur is given by the equation. The probability that both A and B occur is equal to the probability of A times the probability of B. And more generally, this probability formula can be extended so that n independent events occur is the product of the n probabilities of the individual events. So if I asked you what's the probability that if it's multiple things, then you would just multiply multiple things. So an example would be probability that you'll get two tails is equal to 1/2, because that's the one for the first, times 1/2 second, and that's 1/4. All right, let's do some examples of independent events. In a survey at a football game, 50 of 75 male fans and 40 of 50 female fans said that they favor the new team mascot. If one male and one female fan are randomly selected, what is the probability that both favor the new mascot? So the probability of A and B is equal to the probability of A, and we can say this is event A, and this is event B. So we have 50 over 75 times 40 over 50. And then I'm just going to reduce my fractions. I'm going to divide top and bottom by 25, so 2/3. Here the zeros cancel, 4/5. And that's equal to 8/15, which is 0.533, which happens to be 53.3%. Okay. Right. Now, and this works, we use this formula because the events are independent. Choosing a male has no effect on choosing the female. So let's do example 2. A survey found that 46% of parents surveyed say that they read to their children at least once a week. If 3 parents are selected at random, what is the probability that all 3 will say that they read to their children at least once a week? Okay, so the probability that they read to children once per week is equal to 0.46, because that's 46% as a decimal, times 0.46 times 0.46. Now, why am I doing it 3 times? Because, remember, this is the probability that the first parent will read once per week. This is the probability for the second parent. What one does has no effect on the other, and the probability of the third. Multiplying those 3 numbers together, and you get 0.097, which is 9.7%, if it makes more sense to you thinking about it that way. You should always be able to go from a decimal to a percent. Okay, example 3, rounding out this page. During each of the 5 days of a special week, an employee is randomly given one of 10 prizes. All prizes are available each day, and one of the prizes is a $500 gift certificate. What is the probability that an employee receives a $500 prize at least once? We're going to skip this particular one, but you should try it and see if you can get it. So we will skip this one. Instead, we're going to go into what are dependent events. So the definition of a dependent event is when the occurrence of one event depends on the occurrence of the other. Now, where is this practical? It's practical in that, say, there were 20 cookies in a jar, and there's 10 peanut butter cookies, 10 chocolate chip cookies. You randomly select one, and so your probability of getting a chocolate chip cookie is 10 out of 20. You don't place the cookie back, and so you're going to try and get another chocolate chip cookie. Then it'd be 9 out of 19 because you already chose one, and there was one less cookie. So that's when the occurrence of one event depends on the occurrence of the other. Okay. And conditional probability is the probability that something will occur because something has already occurred. And there's a special notation for probability of dependent or conditional probability, and this is how it's notated. P for probability. So the probability of B given that A has occurred, that bar, that vertical bar means given. So this is what the whole thing means. Probability. So you're trying to find the probability of B given that A has already occurred. Now, what if the letters are switched? If you put A/B, it would be the probability of A given that B has occurred. So, just read it that way. Okay. Leaving us with the formula now. So the probability of independent events you just multiplied the individual probabilities. Well, if it's dependent events, then the probability that both A and B occur, so the left side is still probability of A and B, but it's equal to this. It's the probability of A times it's the probability not just of B given that A has occurred. So remember, that's a probability of B given that A has occurred. And I don't need to rewrite that because you have it up above. Now, what if I asked you to solve for this? If I asked you to solve for this and get it by itself, you would want to divide both sides by probability of A. So oftentimes you'll see this formula written this way. So the probability of B given that A has occurred is equal to the probability of both A and B divided by the probability of A. Because all I did was I divided both sides of the equation by probability of A just to get that conditional probability by itself. All right, let's do an example or two. So the table shows the status of 200 registered college students. What is the probability that a randomly selected student is female? The first thing we need to do when we're doing this problem is to have totals. So let's do a line here. We have 140 here. We have 60 here, 80 there, 120 there. We have a total of 200 registered college students, and we knew that. That was given. Now, in part A, what is the probability that a randomly selected student is female? So the probability that the randomly selected student is a female is going to be blank over 200. Well, you look at the female row, and there's a total of 120 females. Okay, and then simplifying, just cross out your zeros and then divide top and bottom by 4, and you get 3/5, which happens to be 0.60 or 60%, if you want to give all three. Okay. What is the probability that a randomly selected student is female, or if female, is a full-time student? So if female is a full-time student, so you want to find the probability. The person's already a female, so we want to look at the female portion, and you want to look at full-time students. So you want to look at this number and that number. So the probability, and the best way to write this, probability of B given A is equal to 40 over 120. So what I did was I did this. I used this formula right here. And the reason why I used that, the probability that the numerator is the probability that the person is female and a full-time student is 40. There's 40 students that are female and full-time, divided by the probability that the individual is a female. So I like using that. So that's 40 over 120, and that reduces to 1/3. Okay, example 5. You randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card is a heart and the second is a club if, here's key words, if you replace, then the process is independent because it's acting like you're starting all over again. If you replace the first card before selecting the second card. So this part A is independent events, and that's because you're replacing the card back. And remember, there are 13 hearts, 13 clubs, 13 spades, and 13 diamonds. So the probability I should get a heart and club is equal to the probability of heart times the probability club. And so that is equal to 13 cards out of 52 cards that are hearts. And since you're going to replace back, you're going to still have 52 cards if you're going to select the second card. And that's 13 out of 52 as well. That reduces to 1/4 times 1/4, which is 1/16. Second one, you do not replace. If you do not replace, then the events are dependent. So the probability of A and B is equal to the probability of just A times the probability of B, given that A has occurred. So the first card being a heart would be 13 out of 52. And the second being a club is you still have 13 clubs, but you have one less card to choose from because you don't replace that card back. So it's 13 out of 51. So this represents club given first card is a heart. Right? And the reason why you have 51 down here is because you didn't replace your first card back. So when you reduce the fractions, 13 over 52 is 1/4 times 13 over 51, which which does not reduce, and that equals 13 over 204. And I don't really care what that is as a decimal. You can figure it out if you want to. Okay, example 6. You randomly select 3 cards from a standard deck of cards, 52 cards. What's the probability that the first card is a heart, the second, then a heart again? If, so again, replacing means independent. Not replacing means dependent. Okay, so the probability that you'll get a heart and a heart and a heart is equal to 13 out of 52 times 13 over 52 times 13 over 52. It's 1/4 times 1/4 times 1/4, which is 1 over 64. That one's not that hard to understand. It's when you have to worry when you don't replace something, because when you're not replacing something, there's things have been taken. So this is dependent. And so the probability that the first one is a heart is 13 out of 52. Since you're not replacing it, you have one less card in the denominator, but you've also chosen one, so you have one less in the numerator. For the third card, there's only 50 cards left, and there's one less heart. So that's how you set that one up. And so this is 1/4 times, I divided top and bottom by 3 for the second fraction, and I got 4 over 17 times 11 over 50. And then what I did was 4 divided by 4 is 1. So I have 11 over whatever 17 times 50 is, and it happens to be 850. So that is your reduced answer. Most students don't like to reduce fractions, and they'll just give this answer as a decimal, and that is totally fine. There is nothing wrong about that. Okay, example 7. Let n be a randomly selected integer from 1 to 12. Remember, integers are 1, 2, 3, 4, 5, 6. No fractions, no decimals, none of that. Whole numbers, but positive and negative. But this one is from 1 to 12. Find the indicated probability. Find n is even given that it is prime. So find the probability that n is even given that it's prime. Okay, so what you want to do is you want to list the prime numbers. And the prime numbers, 1 is not a prime number, but 2 is, because it only has 2 factors. That's what the definition of a prime number is, 1 times 2. 3 is, 4 is not, because you have 1, 2, and 4. 5 is, 7 is, 9, 8, and 9 are not, 11 is, and 12 is composite. So those are your 5 prime numbers. Out of that, the only one that's even is this one. So your probability is 1 out of 5. And the reason why is the numerator is both that it's prime and even, and the denominator is that it's prime. So that is your answer. Maybe I should put the formula there. So the probability that n is, oops, I don't even know why I did that. I'm supposed to make it a capital letter. So, okay, so probability that n is even, given that it's prime, is equal to the probability that it's n is even and prime divided by just the probability that's prime. All right. Next one, probability that n is a multiple of 3 given that is less than 10. So we want to find out all the numbers that are less than 10. Okay, and they are 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you need to figure out which ones are multiples of 3s. So this 3 is, obviously, start with 3. 6 is a multiple of 3, and 9 is a multiple of 3. So that would be 3 numbers out of 9, which is 1/3. And I won't write the formula since we wrote it for the previous problem. All right. Example 8. You and 2 friends go to the same store at different times to buy costumes for a costume party. There are 15 different costumes at the store, and the store has at least 3 duplicates of each costume. What is the probability that you choose different costumes? So let's see, you and 2 friends. So there's 3 of you. So probability A and B and C is equal to, okay, so all 3 of you could pick the same costume. Okay, so you have 15 out of 15, because there's 15 costumes, but you could have the same, times 14 out of 15 times 13 out of 15. And so I just reduced this one. 15 divided by 15 is 1. And so I just multiplied 14 times 13, and then 15 times 15 is 225. So 182 over 225, which is approximately 0.809, which is approximately 80.9%. Right. Suppose your area has 8 different internet service providers and you and 3 friends randomly select your own internet service provider. What is the probability that you all choose different internet service providers? So probably of A and B and C and D, because it's 4 of you. Okay. 8 out of 8 times 7 out of 8. And the reason why it's because you're choosing a different one each time. So 6 out of 8 times 5 out of 8. That equals, and so I cancel that. That's 1 whole. And so I did 7 times, I reduced, okay, here's what I did. I reduced 6/8 to 3/4. And then I multiplied all that together and I got 105 over 256, which is 0.410 as a decimal and 41% as a percent. Right. These last 2 are some of my favorite problems, and I teach it in stats. And this is a tree diagram helps you do these kinds of problems. And that's the best way to do examples 10 and 11. And that's how I'm going to show you how to do it. So yet another strategy of doing probability. Example 10. On a manufacturing line, 20% of all the items produced are defective. Although all of the items are inspected before they are shipped, 10% of the items are incorrectly classified as either defective or not defective. What percent of the items will be classified as not defective? So what you want to do is to make this tree diagram, start off with, here's your item, and put the values on the branch. So 20% of the items, and always change your percents to a decimal so you can do calculations. So that's 0.20, are considered defective or bad. That means 80% of the items are not defective. They're good. So we could put good or we could put not defective. I'll put not defective. Now, reading the second statement, although all the items are inspected before they are shipped, 10% of the items are incorrectly classified. So 10% are incorrectly classified as either defective or not defective. So here you make another branch, and I probably put that one too high. So there we go. That's okay. So 10% were incorrectly classified. So detective was how they were or defective, sorry, is how they were classified. So this would be not defective. And the remaining, remember, there's 100%. So 90% or 0.90 would be defective. So correctly classified. So, okay, for the next one, if it's not defective, so 10% would be defective because incorrectly classified. 90% would be correctly classified as being not defective. Okay, now the question. What percent of the items will be classified as not defective? So you are only interested in this information right here and right there, and you follow your branches. So you start off with 0.20 times 0.10. So 0.20 times 0.10, that gives us 0.02. There you go. You have to put the 0 in there. And then the other one, so this one, 0.80 times 0.90 is what we want. So, and that gives us 0.72. Add those two together, so you have 0.02 plus 0.72, and our probability is 0.74, or 74%. Okay, and in our last example, a high school basketball team leads at halftime in 60% of the games in a season. So let's stop right there. So here's a high school basketball team. Actually, I have room. I'm going to do that over here somewhere, so I'm not like running out of room all the time. Okay, so leads at 60% of the games. So 0.60 leads at half time. Okay, and then remember the remaining 40% would be trails at halftime. Right. The team wins 80% of the time when they have the halftime lead. So here, when they lead at halftime, they win 80% of the games. Therefore, they lose 20%. When they trail at halftime, they only win 10% of the games. They lose 90%. And now the last statement. What is the probability that the team wins a particular game during the season? So you want to follow the win. So this times that, or that times that. So we have 0.60 times 0.80, which gives us, when you multiply those out, 0.48, or we do 0.40 times 0.10, which is 0.04, and then add those two probabilities together. So you have 0.48 plus 0.04, that gives us 0.52, or 52%. So a lot of stuff that we talked about and lots of different examples. Make sure you go over them, and when you're doing your homework, refer back to your notes so you can kind of see which method to tackle your problem. And those are your notes for today. Have a great day, Algebra 2 students.